Good evening, everyone. I think we have most everyone inside right now. So my name is Eileen Anderson. I'm director of the Stem Cell Research Center here at UC Irvine. I'd like to welcome you all to our public lecture this evening. It is my great pleasure to introduce Dr. Irv Weissman. I actually met Irv, my gosh, probably 16 years ago when my lab did not really work on stem cell biology at all, but worked on spinal cord injury. And we started a long series of collaborations that was really transformative, I think, for my research group. Very exciting, moved us definitely into the area of stem cell biology to the point that now I would have to say I'm a stem cell biologist more than I'm a neuroscientist, really. And during that period, I am very grateful to have had the opportunity to really learn from Irv's insight and enthusiasm for science in so much as that's been possible through our contact. Irv has really been a pioneer in many ways, but in one of those ways, he has influenced, I think, maybe not just one generation, but 2 or 3 generations of scientists to think a little bit differently outside the box of working strictly within a laboratory and thinking about translational medicine to a degree where we use sort of the C word, by which I mean cures. And Irv has been definitely a pioneer in this area, certainly within the range of stem cell biology and regenerative medicine, and I think he's going to tell you a bit about that tonight. He is director of the Stanford Institute of Stem Cell Biology and Regenerative Medicine. He was elected to the Institute of Medicine in 1989. He chaired the National Academy of Science panel on cloning in 2002. So his depth in this area is really almost unparalleled. And he was really a significant proponent of the advance that brought us Proposition 71, and what we now have is the California Institute for Regenerative Medicine. So I hope you'll all join me in welcoming Dr. Weissman this evening.
Our body is made up of cells. And most of the cells in our body have a function. So skin cells, you know, must come from somewhere, but they protect us from the environment. What's less well known is that all of the cells of our body come from tissue-specific stem cells. When I say tissue, I mean skin has skin stem cells, blood has blood-forming stem cells, brain has brain-forming stem cells. And if anybody tells you any different, they're wrong. You'll see why, because that's why there are so many fraudulent stem cell therapies out there. They borrowed our word and made a lot more money out of it than we did. Now, stem cell biology is really simple, if you think about it. This is a hidden... Oh, that one doesn't work. Pretend that you're seeing this. There we go. That's a blood-forming stem cell. If anybody has one of these that work, it'd be great. I'd be grateful for it. Don't worry if you don't. So anyway, a blood-forming stem cell, when it divides, it gives rise, on average, in its 2 daughter cells to 1 stem cell. All of the other cells coming from the stem cell, going down to blood, when they divide, they're just heading toward blood. The property of making another cell just like yourself is called self-renewal, and that's limited to the different tissue stem cells in the body. So I know I'm going to go off into jargon once in a while, but I hope I don't, so that now you know that they're... Ooh. I'll just get taken up by this. So now you know that there are stems. Don't worry. You got one? They think this worked? Ah. Talking about aging and stem cells. Which is important, but I don't know if I'll get to it. Okay, it worked. But it hides. All right, there it is. Anyway, where was I? So, stem cells are born while you were and mice are, and other animals are in the uterus very early on in order to make the organs and tissues of the body, so that they come on probably just once in life, and then they self-renew throughout life. And that sounds interesting, but it's also extremely important because it means they're responsible for the development, in this case, of the blood-forming system. Maintenance of the blood-forming system, so that's second. Third is, when things go wrong, you should first think about stem cells. Now, things going wrong could be, you could have a cancer of the blood-forming cell called leukemias. But other ways things go wrong, which I've missed in this slide, but I'll say it, is that even diseases that are late onset can be a disease of a stem cell that, by a change in its genetic sequence by mutation, can outcompete the other stem cells for that tissue. And I'll get to the end of a pretty horrible disease. Judy tells me 10,000 patients, new patients a year, where their whole blood system comes from one aberrant blood-forming stem cell. So I want you to be thinking about the origin, the maintenance, and then when things go wrong with stem cells. We luckily were the first to isolate blood-forming stem cells in mice and then humans. And so a good part of the story I'm going to talk about comes from that. But I do want to say that stem cells are going to be the platform of what we call regenerative medicine. So the important thing is, because they self-renew, you replace bad or malfunctioning or genetically inactive stem cells with a normal one. You just have to do it once. So this does not fit the way that big pharma makes money, so that you remember every day. Self-renewal to them is you renew. You open the pill in the morning, and that box with, I have now, 10 pills I take in the morning, 8 at night, just to stay alive. Well, they love that because you pay every time. So right from the beginning, trying to make stem cells into a therapy bumps into how people make money from medicine. And I'm going to say this over and over again, and pretty soon everybody will be tired I say these things. But it turns out to be the critical barrier to turning stem cell discoveries into stem cell therapies. So we'll get back to it, or at least I will. Blood-forming stem cells, even now, even though they aren't used purified, they offer curative therapies for blood diseases. So as I go through the talk, I'll go into how they're done now, but also how we plan to do it in the future so that everybody can get a stem cell transplant and avoid the kinds of chemotherapy or radiotherapy that doctors usually give to get a blood-forming cell transplant to work. Each tissue has its own stem cells, so we can consider every organ to be potentially replenished by the healthy stem cell of that organ. And finally, we'll talk about cancer stem cells, because cancers don't come from Mars. They come from our own bodies. They come from tissues that have stem cells and progenitors, and then the daughter cells. So we discovered the way to isolate blood-forming stem cells first in 1988. And then I formed a company with my colleagues, and we published that we had human blood-forming stem cells in 1992. The company was called Systemics. And we started off, I borrowed this slide from Anishka Chekovitz, who was a student of mine about 10 years ago, just to say, if you were somebody who wanted to take a weak light and turn it bright, right? Treat diseases, you're not going just for orphan diseases. You have a chance to cure somebody with a one-time treatment of an incurable disease. Think sickle cell, thalassemia, severe combined immunodeficiency, and this is blood stem cells alone. So this is not a minor treat. So when we began the field, we knew that the blood-forming tissue, which in us is bone marrow, but included, when we were born, umbilical cord blood. In the fetus includes the fetal liver and the fetal bone marrow. It's a mixture of cells. 1 in 100,000 to 1 in 200,000 of those cells is the blood-forming stem cell. All the rest are in a transplant as currently done today, even though we isolated the blood-forming stem cell 30 years ago. So we'll get into why that happens. But the first thing we had to have was a way to isolate just the right cells. So in this cartoon, this is not a device that really exists. You got T cells that are immune fighting. If you don't have T cells, HIV kills you. Cancer cells, if you have widespread breast cancer or lymphoma or myeloma, there is no doubt that you have lots of cancer cells that have spread to your blood-forming organ. And so if you're going to try to use that for a therapy, just remember you're giving cancer cells back. And other cells. And then this rare stem cell. So this is a cartoon somebody drew for me. We isolate pure stem cells. And they are at least 250,000-fold depleted of cancer cells and T cells, the major problems in human bone marrow transplant right now. And I'll just stop for a second to say, before we isolated and named the stem cell, people who did the transplants of bone marrow or mobilized blood called themselves bone marrow transplanters. Within 2 years, they called themselves stem cell transplanters. How did they change what they did? They changed their name to stem cell transplanters. You got cancer back if you had cancer in it. You got T cells in it if you got it from a donor. No change whatsoever. And that's a problem. How many of you know pre-meds or knew pre-meds in college, right? So what was the prime thing that worried you about pre-meds, including maybe yourself? You memorized, and you had the discipline to memorize. And you memorized and spent more hours memorizing than everybody else. And then you thought what you memorized was true. But what you find out when you do research is it's hardly ever true. But all of the doctors we have out in the community were memorizers, and the very best grade getters of all, is this right, Judy, were the bone marrow transplanters. They beat everybody. So they just changed the name to stem cell, and that was it. And then they taught everybody it was stem cell, and they published stem cell. The only problem is it never was stem cell. Back in the 1990s at the company I co-founded called Systemics, we isolated cancer-free stem cells. Nothing was in the tube but stem cells. Or mobilized blood from women who had metastatic breast cancer. Now the idea was that if you could just increase the dose of chemotherapy that kills cells, almost all dividing cells that are in front of the drug or in front of the radiation beam, if you could raise the dose, you would kill more cancer cells in the body. Simple quantitative relationship. The more drugs, the more of the combinations of drugs, the fewer cancer cells in the body. Could we get to a point that we killed all the cancer cells in the body? No, because we destroyed the blood-forming system first. So if you go back to Hiroshima and Nagasaki, in retrospect and in experiments that followed, the people who died at the lowest dose of a radiation that killed died because their blood-forming system was destroyed. They couldn't make platelets to clot blood. They couldn't make what's called neutrophils to fight bacterial infections. And they either bled out or died of infection about 15 days after radiation, when all of the cells that would have been developed from stem cells die. So it was obvious that you would move this field to chemotherapy and oncology, because you want to increase the dose, but the limit is, can you restore the blood? So we did the experiment, and I'm going to show you the outcome many years later of those women who came to Stanford to get a mobilized blood transplant from themselves, either the whole population of cells contaminated with their cancer or the others. And I got to say that I can teach this concept that it might be better to give back cancer-free stem cells than cancer-contaminated. I can teach it to kids. I wrote a kid's book about it. They know it. I can teach it to high school, college, medical students. I cannot teach almost anybody who's a bone marrow transplanter or a breast cancer oncologist. I go to Judy all the time. She'll raise her hand at some point. I said, let's go ahead and do it again. She says, well, the breast cancer docs won't do it. So now let's see what's missing, because they won't do it. Now it becomes serious. 50,000 women a year in the US get metastatic breast cancer. This is the overall survival of people treated in that therapy. 74 patients who got back mobilized blood, as everybody was doing in the 90s. Half of them were dead at 26 months. All of them are dead now, 20 years later. Most of them were dead 11 years later. In fact, I remember that at 3 years, only 6% of those patients were alive and didn't have known breast cancer in the body. So that's no better than what the docs have been giving women with metastatic breast cancer for 30 years. It is no different, and it is no better now, despite all of the advances. Now, I don't read the literature thoroughly, so some smart aleck can get up and say, you're wrong. We now have a drug that'll treat metastatic breast cancer. But I'm also a cynic. I doubt it. So after we gave these high-dose, lethal combination of drugs to women and restored them with their own purified stem cells, and I got to tell you, it was a very frightening moment. I was there. Judy, I think, was just an assistant professor. We were giving back to a woman whose bone marrow and blood-forming system we had killed off instead of liters of her own bone marrow and mobilized blood, a thimbleful of a clear liquid that contained stem cells. 10 days later, her neutrophils were back. 13 days later, her platelets were back. And all we gave was her cancer-free stem cells. And this is the overall survival of those patients. Half of them, by extrapolation, dead at 10 years instead of 2 years. So those women gained 8 years average survival. And it's not a therapy now. 1/3 of them are alive today. That first woman, the bone marrow transplanter at Stanford, said, Irv, this is so sad that this is your first patient because I've rechecked the histology, meaning the microscopy, and this is one of the worst, most invasive, most malignant ones. She even got an effusion of cells back in her chest cavity that had to be taken care of. I talked to her this year. She just finished 30 years as a second-grade teacher in California. She raised her kids and, of course, all of the local kids as well. She never saw a doctor again for breast cancer. She didn't spend the $50,000 to $80,000 that oncologists make per breast cancer patient, taking them to an easier death. I'm saying this strongly, and I'm not a snake oil salesman because I don't own this, because this is a discovery that should have been translated immediately. It should have been a treatment for everybody. But the company that I founded, Systemics, We later formed an intermediate company called Celerant because a large pharma had bought our company for a lot of money. And if you were just an investor, you were happy because $10 million investment turned out to be almost $800 million in the sale to this large pharma. What I didn't know, what I didn't suspect, and you all need to know, is the large pharma wasn't buying just our property for the future. They were buying lots. And in the year 2000, which was right about here in the curve, they knew and we knew there was a difference. They shut it all down. They didn't call me up to say, please take back the therapy and run with it. In fact, when I tried to restart the trial in the early 2000s, we were on the edge of doing it, and the venture capitalists in the second company asked 2 local Stanford doctors, would it work? And they said no. They didn't know the data, but they had memorized their way to be good doctors. They thought that their information was the right information. Have I pounded this enough? The problem with big pharma and biotech and venture capital is that sooner or later the money owns the property, and oddly enough, the money thinks it understands the biology. And the theme of what I'm saying is the biologists who make the discoveries need to be there all the way through early clinical trials. Otherwise, the simplest thing that looks like a risk, and you shut it down. They happen to get a drug that you could take by mouth for a pretty rare leukemia, and it makes them $2 to $4 billion a year. So they wanted to focus on it. Now, let me just, before you think I'm a communist, the function of a company everywhere is to make a profit. If you don't maximize profit, your shareholders rightly will say, you're making decisions with my money that's not appropriate. So we have 2 competing problems. We have those of us in the biomedical research enterprise who think that we are doing studies to advance medical science for people. And we have businesses who are driven to make a maximum profit. And we somehow have thought that they go together. Well, they don't go together. And as I'll describe at the end, if I ever get there, that in fact there's a reason they don't go together, and there is a way we can get around it. And in California, there's a way we've shown how to get around it. But I'll get back to that. Ooh, I got 2 slides at once. Okay, now, we were wondering how stem cells, blood-forming stem cells, can go wrong to cause leukemia. And Ravi Majeti, a faculty member now, but he was my fellow then, and Max Jan and a number of us had found that we could do the DNA sequence on somebody's leukemia and actually know which genes were mutated to make the leukemia. And so we made ways of probing for each of those genes that had happened in that person. And we took single blood-forming stem cells, that's what this is supposed to look like, and we found the cell that had just the first mutation. And the amazing thing was, that single cell was probably no more than 1 in 100,000 cells of bone marrow. It was in one bone marrow cavity when it started. We could stick a needle in any bone marrow, pull out the stem cells, and find daughter cells of the one that had sustained that first mutation. The total number of stem cells in my cartoon didn't increase, but the cells that gain an advantage over the other stem cells outcompete the the other stem cells, expand at the expense of the normal stem cells. We even know what the niche, the home, looks like in mice for those stem cells. So we can start the process of asking, how could one cell with a single mutation that changes its behavior outcompete a normal one? At least we're on the road to try to find it. Now, current therapy is not aimed at the cancer stem cell that comes out, but at all of the other cells that get killed by chemo or radiation. So if you see a 90% drop in all of the cells that you call by eye leukemia, even though only 5% of the cells are leukemia stem cells, if you see that 90% drop, that becomes a drug. But if it doesn't kill the cell that accumulated all of the mutations slowly, then the tumor will come back. So you have to eliminate the cancer stem cells. Now, sitting in the audience is Mike Clark, the first person on Earth to propose and then show in human breast cancer, oddly enough, there are cancer stem cells, and if you don't kill them, the cancer comes back. Raise your hand, Mike. Just a little bit. There you go. Yeah. Right? So that's why we recruited him out of Michigan. Second point I'm going to make is that each of those changes, those mutations, you increase what's called the clone size, the daughters of the single cell that had the first mutation. Well, those mutations might help them be stem cells, but they're also getting to be more and more of your blood-forming system. And hopefully very soon, I'll talk about the diseases that can happen when your normal stem cells are replaced by the daughters of a cell that can outcompete stem cells but has a mutation. So, can the mutated pre-leukemic blood stem cells form a disease? The ones that are starting to dominate. So some mutations make them more competitive for stem cell homes. And in one disease, this was discovered by a medical student working in my lab, Wendy Payne. She now has mistakenly moved over to Judy Shazuro's lab, but what the hell? She discovered, when she looked at the bone marrow of people with this disease called myelodysplastic syndrome, people who don't make enough red blood cells, or platelets, or granulocytes, the blood-forming stem cell that had the single chromosomal change that signified this disease had completely taken over the bone marrow. At least 98% of all of the places we looked, the stem cells were from the single cell. Now, they were people my age, myelodysplastic syndrome. They come in and on a blood test, they don't have enough red cells or platelets or granulocytes. And they will die of that disease unless they get leukemia, which does follow on, and I'll talk a little bit about that later. But the important point is, this is the precedent, that a single stem cell that has the property of migrating and competing for stem cell homes can take it over and cause a disease even if you don't know you have that early process going on. One of my other former med students, Sid Jaiswal, has just published 2 papers in the New England Journal of Medicine that when he looked at otherwise apparently normal people, over 40, 10 to 30% increasing with age, had clones derived from a single cell that had a single mutation. So it had already taken over 10 to 40% of their bone marrow. And he's found, in a way I don't quite understand yet, and he doesn't either, that that is the highest risk factor of dying of a coronary artery occlusion or a carotid artery-induced stroke or an abdominal aortic aneurysm. Except for maybe smoking, this is the highest risk factor. So we have to pay attention to starting to understand how to know a clone in the blood-forming system. And I want all the scientists in the audience to think, if it happens in blood cells, it happens everywhere. Mutations aren't coming in like cosmic rays and saying, where's the stem cell? I'll mutate that. Every cell is at risk. In the blood-forming system, almost all the cells except the stem cells will die out of a natural aging process. So we only see long-term effects if it's in a stem cell because it's in a self-renewing cell. It doesn't cause self-renewal, but it's in a self-renewing cell. Well, as Eileen said, we discovered brain-forming stem cells. Brain-forming stem cells are active throughout life, no matter what somebody in Northern California says. There's no doubt about this. And they continue to generate in part of the brain things that allow us to put together perceptions into short-term memory, at least one part. Can you imagine if they compete for niches and now you have an aberrant stem cell, that's going to slowly have an effect on the whole system. So I want at least the scientists in the crowd to think about the lesson from leukemia was there only because we could isolate the cells, get pure cells, and ask who they were and what they did. But I'm expecting the lung, the bladder, the liver, the brain will have late onset diseases from early onset mutations. At least Brian's nodding his head, so I'm halfway there. Eileen is kind of wavering on it. Okay, when we compared leukemia stem cells in humans, which we could isolate pure, we did that in 2000, with normal blood-forming stem cells, so that now you have cells that ostensibly are very close to each other, but now you could ask, what RNAs do they make to make which proteins? And what's different in the leukemia than the normal? And amongst the many differences we saw was an upregulation of a molecule called CD47. Now I have to apologize. Immunologists invented this term CD. It doesn't mean anything worth remembering. But it is a code so that they can talk to each other and you will not know what they're talking about. So we discovered this one was on every leukemia mouse in human. So we want to know what it did, and I actually, for the first time, probably read a paper that was relevant for the time. And Oldenburg and Lindberg in Sweden had shown in mice it was an age marker on red blood cells. And it was an age marker because it was a don't eat me signal for the scavenger macrophages that patrol the body all the time looking for diseased, old, dying, aged, dangerous, inflamed tissue cells. So there's the eating cell. It's going to eat that cancer cell. It sees something on that says, eat me. But it's stopped by a dominant, don't eat me. So this molecule in a cancer cell paralyzes the macrophage, so it can't engulf and eat and kill the cancer cell or the old red blood cell, and so on. So we made antibodies that blocked it. Somewhere it'll show up, I know. There it is. And now the cancer cell comes, and the don't eat me signal is gone, but it's still got the eat me signal, and it engulfs the cell. So this is just one of those experiments where you don't have the don't eat me signal. You see these clusters. These are all cancer cells being eaten, leukemia cells being eaten by the scavenger cell. We had to wash away all those green leukemia cells to see that the eating cells were empty if they had the don't eat me signal there. Then wondered if there was a difference in cancers. And we found that every cancer that we looked at overexpressed the don't eat me signal, not just on the cancer stem cells, but all of their daughter cells as well. This is, Mike Clark gave me directly from a patient's sample, the cancer stem cells for the breast. We put them into the breast, the mammary gland, of an immune deficient mouse. So it had no immune apparatus to kill the cancer on its own. But now we could ask, does its don't eat me signal exist that prevents the phagocytic cells, the non-T cell, non-B cell, non-natural killer cell for the audience? And those that were later treated with the antibody that blocked the don't eat me signal of the cancer was eaten and removed. So, just think about that, Judy. Cancer-free stem cells. Cancer-free stem cells can get rid of most of the cancer. That time between 2 years and 10 years, median survival, probably means there were less than 1 million, less than 100,000 cancer cells left in the body of those who died of the cancer at the end of high-dose chemo before rescue. So now the problem is good because our treatment of even breast cancer, which was great, did not get rid of the breast cancer if it was a large cancer already. Couldn't keep up with it. So we showed in glioblastoma, breast cancer, ovarian cancer, bladder, all of these with samples that we got from the Stanford oncology and surgical oncology surfaces, that thanks to Mike's pushing, we transplanted from brain to brain, breast to breast, ovary to the peritoneal cavity where it spreads, that all of these cancers have the don't eat me signal. All of them we can get rid of a lot of the tumor with simply the antibody that blocks the don't eat me signal. All of them. It's easier to get small tumors. It's easy to get newly seeded spread cancers that are small than the large one. And I'm going to show you that it synergizes. I hope I show you. Yeah. With other anti-cancer antibodies, all of them, to more efficiently remove the cancer. Now, anti-CD47 antibodies are in late phase 1 clinical trials. So here's a cartoon of that scavenger cell. It has a receptor for the don't eat me that's blocked by antibody. And we know that an antibody used to treat lymphomas called rituximab leads to the eating of the lymphoma by macrophages. Oncologists will also tell you, I don't mean to totally disparage oncologists, that it really works because there's a cell called a natural killer cell that has that same receptor, and then it kills with a package of enzymes, one of which we discovered, that explodes the cell. We wanted to know, does blocking the don't eat me signal synergize with this rituximab in not only samples of lymphoma, but patients with lymphoma? So here's that experiment. This was a highly malignant called diffuse large B-cell lymphoma. And we transplanted it into a mouse, into many mice, directly from the patient. And the tumor grew if we didn't treat it. But it didn't grow if we treated it with our blocking antibody to CD47, the don't eat me signal. It didn't go away either. If we treated it with rituximab, as in many patients, the growth is greatly slowed, but it still comes back. But when we combined the two antibodies, we got rid of the tumor. Now, in a clinical trial, that was carried out at Stanford on this kind of lymphoma in patients who you could no longer give rituximab or chemotherapy or a combination of rituximab and chemotherapy to get any response at all. Half of the patients with DLBCL and even more with what's called two-hit follicular lymphoma for the people. They're just, think of it as aggressive lymphomas. Half of them respond, and the 33 out of the 40% with DLBCL are in a complete remission now, 6 to 18 months later. And it's actually 43% of those with that follicular lymphoma. Now, I left out something that I meant to talk about early, but I'll talk about it now. Given my experience with the breast cancer treatment, rescuing them after high-dose chemotherapy with stem cells, I became very suspicious of startup companies and big pharma. So when, as Eileen answered, I was head of a National Academy of Sciences panel on cloning, which really meant at that time taking the chromosomes from a healthy body cell, putting into an egg that had its chromosomes removed, and make a pluripotent stem cell line out of it. The government, as soon as we made our report, said we're not going to fund that. And we're not going to fund any fetal tissue research. Our government. Well, soon after that, parents of diabetics, children of Alzheimer's patients began calling me because I was head of the panel. I was on TV and stuff like that. And they said, does this mean that my child won't have a therapy that might have developed? I said, yeah, that's what it means. If we can ever make insulin-producing islets and use the blood-forming system in a way I'll show you in a minute, won't work. So the people demanded that we do something. And we were all very disorganized in 2001, 2002, about how we would do this. And then, luckily, Robert Klein was suggested to us as somebody who had a child with type 1 diabetes and a mother with Alzheimer's, and he was a demon at social experiments that could require local government funding. So we gathered together and we wrote Proposition 71. Proposition 71, you may remember in 2004, when Bush was winning the second term, was a constitutional amendment and an initiative in California. So the people could vote on it. And Bob Klein had the genius to make it an initiative, not something you take to the legislature, because the legislature likes to fiddle with money every year, and they got every reason to decide this or that. So he made it a bond issue. I got it. It's a bond issue. 40 years, you pay the bond back, but you pay out the money for 10 years. $3 billion. And I got to write part of it, and that included the agency would be able to fund through early phase clinical trials those selected discoveries, even at academic centers that didn't have any professionals yet, like drug company people or like biotech startups. And this CD47 program got funded. $20 million later, after the funding of a mouse antibody, a mouse experiment, we filed initial new drug applications to the FDA and to the English equivalent and began these clinical trials. I think there's never been a biotech company, not any I've dealt with, that have filed an IND after $20 million total expense. And the difference was we kept the discovery team together as they went through the bumps that happen in early stage development for clinical trial, and then when you do a clinical trial. I could tell you a lot of stories about it, but the take-home lesson is that the California Institute of Regenerative Medicine, funded by Proposition 71, headed right now by Jonathan Thomas, he's somewhere in the audience, yes, does this. Right, there he is. Does this every day. And none of us who wrote it, I tell you, have any preference in getting our grants approved. I've had many disapproved. It's okay. And also, by the way, we included in that if anybody made money out of this, depending on how much money CERN put in to fund it, whether it was patentable or not, the university that got the royalties from the patents had to share it in some way with the agency that funded it. You can't do that with federal funding because of the Bayh-Dole Act. And I'm not going to go on there. I'll just leave it there. But I needed to say that we found a way, I think, to skirt the valley of death. And that is clearly to keep the investigators who made the discovery in line without a profit motive in order to get that discovery to the place that you're beyond the risk that a large pharma like the one that closed down the blood-forming stem cell transplant field completely and didn't tell anybody could do. This is breast cancer. This is Herceptin. It's also called trastuzumab. Same thing. A breast cancer grows. We treated it for that time with our antibody. Then it grew with rituximab. With Herceptin, trastuzumab. Together, we got rid of it. So this is what we're talking about eventually, if that's all that we have to worry about. Now, when we discovered the don't eat me signal, we also discovered the eat me signal, and I'll just say the word and then stop. It's called calreticulin. It's got such an unusual biochemistry for that to be an eat me signal that I would spend the rest of my, an hour and a half left before I got to it. But I'll just say with that discovery, we could look at every disease for don't eat me and eat me. With Nick Leeper, we've shown mouse and human atherosclerosis is a disease, not, as everybody says, because you eat too much fats, because I eat too much fats. It's not just that. If you look at the arteries, or the coronary artery, or the carotid artery, you don't have the whole artery closing off in that disease. You have little bumps, which Nick Leeper and I have shown are just like the pre-leukemia single mutation of proliferating smooth muscle cells that would have become a cancer, except they killed you by closing off your coronary or your carotid, right? So it's not a different disease. Biology has some commonality. They turn on, the successful clone of smooth muscle cell turns on the don't eat me signal because they had to overcome the eat me signal. And it wasn't intentional, I'm sure. It just happened. Scar-forming cells, Gerlinda, Vernig, and I have shown exactly is the same in pulmonary fibrosis, idiopathic it's called. Idiopathic means an idiot doesn't understand how it works. Scleroderma you've heard of. Liver fibrosis. My son had exactly that disease, had to have a liver transplant. Post-surgical adhesions. There are some people who have to keep going back in because after surgery they have fibroblasts that clog up. In all of the cells, in all of these two, the pathologic, the dangerous cells express CD47, don't eat me, and calreticulin, eat me. And if you block the don't eat me, you have a chance of clearing it. So we're not just looking at this. So anyway, the last part is going back to stem cell transplants. That's where I started, blood-forming stem cell transplants. And we knew that we wanted to be able to transplant donor blood-forming cells without the cancer or without T cells that would react from a donor against the host. So let's say that Eileen put a skin graft on me. I would reject it because she's not me. And my T cells would reject her skin on me. If she needed a bone marrow transplant from me, my T cells that like to reject her skin will go to her skin and reject it. And my T cells that would reject her lung go to her lung and go to her liver. And as Judy can tell you, those patients are the hardest to treat because that's called graft versus host disease. And Judy and I showed that if you purify stem cells, you can get the benefit of stem cells without graft versus host disease. Published that, only about 20 years ago. So give it time. The oncologists and breast cancer doctors might read it someday. The other thing that Kim Gandy and I and Judy and I showed is that if we transplant blood-forming stem cells to recreate a blood-forming and immune system from the donor, it won't react against its own heart or liver, lung, or insulin-producing islets. That's called immunological tolerance. Judy talked about a case of it, and I talked about another case of it today, all in mice. But we're going to go there, that we're going to get blood-forming stem cells and organ transplant from the same donor. But the problem is that in order to get a bone marrow transplant to work nowadays, you give a lethal dose of combination chemotherapy and or radiation. And very old and very young and very fragile patients can't live through that. So it's not a universal therapy. Judy and I showed, and I'll just say this without going through the data because it is data. We cured juvenile diabetes in mice by replacing the diabetes-prone blood-forming and immune system of those mice, genetically autoimmune. They make T cells that kill their insulin-producing cells. Straightforward. By putting in stem cells from a diabetes-resistant strain, even a closely related strain. That's what all that data shows. And if you waited until after they were diabetic, you could co-transplant in a very small pilot experiment both stem cells and insulin-producing cells from the same donor into a host that had been kept alive with insulin pellets, I think it was. Okay? So now we're talking about a lot of diseases. We went back and showed in lupus. There's a mouse strain that gets lupus that looks just like human. At any stage of the disease, we could stop the autoimmune attack simply by replacing the disease blood-forming and immune system with that which had resistance to that disease. I like to show this one because this is the experiment that Eileen and Brian did. They created a mouse, an immune-deficient mouse, which had a contusion injury, not a slice, but a contusion injury. And what T10 was it? Thoracic vertebrae. So if that's the spot that loses blood supply because of the injury, the cells that have their cell bodies in that region that can't be nutritious die. But not necessarily the motor neurons in the head or the sensory neurons in the foot. They still have processes that go through. Their cell bodies weren't there. So when we transplanted human fetal brain stem cells into them above and below the lesion, if I were to show the movie, we cured them. And in many patients that we tried with thoracic injury or cervical injury, they were cured, or at least partially cured. for the time the transplant was there, but I'll just say, for business reasons, somebody said, I read in a textbook, that the brain and the spinal cord are immune privileged sites. We can get a lot more patients in. We can make a lot more money if we just stop the immunosuppression. And sadly, because now we've checked back, those that had recovered sensation from a thoracic injury have lost it again. Those who had moving their fingers with cervical injury, and many diseases. So, I may not be a communist, but I'm not happy about leaving it to business and business decisions what makes it to therapy for human and what not. We're getting near the end. Last part is we needed to get rid of all that toxicity of chemo and radiation. And with a student named Anishka Chekovitz, we started off, and then with Judy, we made combinations of antibodies. So if a radiation kills a blood-forming stem cell, we found an antibody that eliminated a blood-forming stem cell. If radiation killed the T cells that would reject a graft, we found antibodies that got rid of the T cells, and so on and so on. They all needed that antibody to CD47 to make them more efficient at eating and killing the cells that were targeted. So now we have a new method of antibodies only. As Judy would tell you, this is an outpatient treatment. You don't have to go down into an intensive care unit. In the first clinical trial, Judy has talked about, I don't know if it's publicly known. Judy? On the severe combined immune deficiency patients? Okay. So, with antibodies to stem cells alone in severe combined immune deficient patients, funded by CIRM, they got the antibody first, and then they got the enriched transplant full of stem cells. And for the first time, at least in a couple patients' lives, they make their own antibodies. Now, you read about it every day, the other aspect, because it's so sexy. Let's do CRISPR gene therapy to fix a single gene at a time, and it's just as good. You use self-stem cells. But my hope is that we have an open and not competitive advancement of both ways. Both require stem cells, so I'm happy. Fix a gene, give a healthy stem cell. I don't care. But those you can expect to be in the headlines, although gene therapy always, for some reason, crowds out the front page. But we get there somewhere just before the comics. We use monoclonal antibodies to get rid of the stem cells. And just as a final point, in mice, we've taken mother-to-child kind of transplants of blood-forming stem cells after antibody clearing, and we put a heart transplant in. We happen to use newborn donor hearts because you can put them in the ear and you could watch them beat. That's what that's supposed to do if I'd remembered how to make it look like it was beating. And it's a permanent cure. Yeah, I'll show you later. Okay, so limited or no use of radiation or toxic drugs is the future. Not for cancer, because you still need to kill off the cancer and you need to have some T cells killing it. But for regenerative medicine, all of regenerative medicine, this is where we're going. No radiation, chemo, pure stem cells. You get rid of the host T cells, other immune cells with antibodies. You co-transplant the tissue stem cell, let's say a brain stem cell. From the same donor, we have a blood-forming stem cell, and we will do it. In the far future, the reason that we object to our government telling us not to do embryonic stem cell research is that instead of waiting, as my son had to, for somebody to die in an accident so a liver would be available, and a team with the logistics to get that liver out within an hour of a violent death in New Orleans, instead of waiting for that, We will have cell lines that make a liver stem cell and a blood-forming stem cell, a brain stem cell and a blood-forming stem cell, a lung-forming stem cell, and so on. So that's where the future is. And I'm not going to go into that. These are the diseases that can be treated, but this is my bottom line. Here's where we make discovery. Here's where discovery gets lost. It's called the Valley of Death. We filled in the Valley of Death. In my life, it was just big pharma. Then it became venture capital and biotech startups. I've tried it. I've tried it many times. Almost inevitably, that's where it dies before it gets to clinical trials. So we've got one bridge across the Valley of Death. It's only in California, and we know it works. It may not be perfect, but we can make it better next time. Right, Jonathan? We can get rid of those things that didn't work and improve on those things that do work. And so although this isn't an advertisement for 2020, it should be. Thank you. Don't be shy.
It's a free-for-all here. Don't be
There
shy.
is nothing such as a stupid question.
Or even a bad one.
Irv,
He's got, oh, okay, go ahead.
would it be at all useful if I just spent a couple minutes about the future of CIRM and how these folks could help?
Sure.
That would be fantastic.
That would be great.
Okay, so Eileen, want to say that this was a fantastic conference today. For those of you who were able to go to the sessions, this was an absolute all-star lineup of cutting-edge A-team researchers doing things that are positively transformative and are going to make tremendous differences to whatever conditions they're doing research on and to patients and their families who have those conditions. And it's really fun to go listen to them and to understand how science is just changing the face of medicine and how much that's going to make a difference for all of us here, because everybody's family's got something and regenerative medicine will speak to it at some point down the line. May take longer for some things than others, but nonetheless, it is going to happen. Irv talked about our institute, the California Institute for Regenerative Medicine. I had the privilege of succeeding Bob Klein, who was the person who Irv mentioned, came up with this idea along with Irv and a number of pioneering stem cell scientists back in 2004. I've been the chairman of the board now for 7.5 years, which is hard to believe, but it's been a tremendous privilege. We had $3 billion. That sounds like a lot. And in the years since CIRM became reality in 2004, we have put out over 1,000 grants covering research on about 40+ conditions or diseases, including all the big ones: cancer, heart disease, diabetes, neurological disorders, etc., all the way down to a number of rare or so-called orphan diseases. And this work has created a pipeline of projects that is working its way inexorably along into clinical trials. And when you get through the clinical trials, at the end of that, if all goes well, you're able to commercialize a product, and that product will change the world. We have a few things already that, even though they're in clinical trials, we now can tell are going to actually be cures for a number of diseases. And for those patients that have those conditions, when you find a cure, that's a huge deal. So I like to say everything we're going after is, just think about Jonas Salk and polio and how that transformed the world. He cured the condition, and that's what we're trying to do with the regenerative medicine work that you all enabled through your vote in 2004. The $3 billion, which I said sounds like a lot, is about to run out. And the projects that we have enabled, many of which were discussed here at the symposium today, and others Irv has brought up and that he's working on. And by the way, if the CD47 works to its greatest potential and Irv ends up curing about 10 types of cancer, that's going to be quite something. And so we're obviously heavily pulling for that, as we are for the work of everybody here who presented, and all of you scientists here who are doing work at UCI, which is a fantastic facility doing tremendous pioneering stuff. And really would encourage those of you who are interested to look more into what they're doing here, because you'll just be blown away. It's fantastic. In any event, we're going to run out of money. And if we run out of money and all this great stuff that we have enabled through our funding, courtesy of you, a lot of it will not be far enough along to attract the big money at the end of the rainbow, which is the big pharmas, the biotech, big biotech, or the venture capitalists who will take the work that the scientists have done and move it through drug development and commercialization. And if we hit the wall on this stuff, and a lot of it isn't to that stage yet, the research will have been a great academic undertaking, but a lot of it will be for naught because there's nobody to step in to fund what we fund. So we need to refund and re-up what we're doing. My predecessor, Bob, and I'm now speaking on behalf of him, not CIRM, plans to come back to the ballot in November of 2020 with a re-up measure where he's looking to get, as opposed to $3 billion, he's contemplating $5 billion. And again, that sounds like a lot. But he and I were talking about it, and I said to Bob, I said, Bob, bond measures on the state ballot, we just had one, right? They're all huge. Nobody pays attention to the numbers. $3 billion, $9 billion, $12 billion. Nobody cares. The question is, do they like the subject matter? And so it's up to Bob, who will be running this campaign if the polling in 2019 shows enough support in the public to do so. It's up to Bob to get the message out to the public about the great value that has been created by CIRM and the wonderful scientists that we've had the privilege of funding. And if that message gets out sufficiently, and it goes to the ballot in November of 20, it only needs 50% plus one. When you do a state bond measure, that's all you need. Those of you who are aware of local bond measures, school district, et cetera, you'll say, wait, well, those are 2/3. That's really hard to get. That's true. But this is a state measure where you only need 50% plus one, which is an enormous difference and gives us a great competitive advantage. Prop 71 in 2004, at a time where there was a lot of controversy about the subject matter, embryonic stem cells, controversial, was a time where the economy was down, where you wouldn't think that people would vote to increase taxes to support something like stem cell research, ended up passing 59-41, an overwhelming victory. If you look at the history of bond measures in California, you'll see they pass at the state level 90% of the time. I bet most people here didn't know that. Regardless of size, 2 billion, 9 billion, whatever, or subject matter. In fact, the LA Times did an article back in July that gave that stat, and they said you wouldn't believe some of the things that get funded at state bond measures. For example, stem cell research. It's in this article. Thought that was pretty cool. Anyway, last thing I'll say is it's going to take a great effort by everybody to make sure this thing passes, to get that additional funding that'll keep CIRM going and this research funded for 15 to 20 years beyond 2020. We purposely put it on the November 2020 ballot if it's going to go anywhere, because healthcare should not be a political thing, but the sky is blue is political these days. And as it happens, and this is not a judgment on your political leaning, but bond measures tend to get higher turnout, higher percentages when you have more Democrats voting. November 2020 is the presidential re-election just guessing, it's going to get a pretty high turnout of Democrats in the state. So please keep an eye out for this, and if you have the opportunity to help in any way to get the word out of the value that all of these great scientists today have described to you, please help. We need it, and if we're successful in 2020, we will set up the transformative research for the next 15 to 20 years that you will look back 20 years after that, and this era will have been a huge turning point in the development of cures for many currently terrible incurable diseases. So please help, coordinate through Eileen, everybody here, and we look forward to working with you, and onward to victory in 2020. Thanks.
Great talk. I have two small questions. One is CD47 a signature for a malignant? Is cancer stem cells gets upregulated with malignancy or not? Is just a normal...
Say it again.
Sorry, is CD47 like a feature of malignant cancer stem cells or hematopoietic cancer stem cells, or is more a normal stem cell or any type of other cell don't eat me signal, and you need maybe both eat me to not eat me?
47 is upregulated on every cancer by the time we see it. In the pre-cancer development, it isn't up yet. The normal stem cell depends where and what it is. So a blood-forming stem cell sitting in its home has very low levels. It's not being surveyed by macrophages. But just as I said, a leukemia or a pre-leukemia or a myelodysplastic stem cell can go from one bone to the next. Before they go out into the bloodstream to get here, they put on CD47. And then they shut it back down when they get to their new place. Cancers don't shut it down, and we have a pretty good understanding why they don't. But it is a constant feature. Now, what I said to the audience today, and what is something we have to pay attention to, we've found 3 more don't eat me signals. And we are investigating whether they will be dominant in that other 50% of patients who didn't respond to our therapies. So we still have a ways to go.
And the other question is, do you envision to have co-transplantation therapies in the future where you have, for example, promote immunotolerance with hematopoietic stem cells together with, for example, neural stem cells in the spinal cord?
Say it one more time slowly.
Sorry. If you envision to have co-transplantation therapies between, for example, hematopoietic stem cells to induce immunotherapy and your stem cells after spinal cord injury.
Yeah, I think what we want to do, obviously, is to have first a donor that matches enough that when they make immune cells to protect the body, they'll protect self, all the rest of the body. So that puts a restriction. It can't be any donor, any host. Even though we can transplant pure stem cells, at least in mice, any donor to any host by this antibody conditioning. But if you think about it, although it's very unlikely that in a small family you'll have a complete match at the one gene locus that determines major immune response against it, every family has somebody who has one that's from the mother and one from the father. So the mother or the father or the children or siblings, most of them could be donors. That will be a dramatic change. When eventually we can get blood-forming stem cells from embryonic stem cells, or what are called induced pluripotent stem cells, we can then set up banks that have at least one share of the gene for everybody. Shinya Yamanaka, who invented the method to reprogram cells, did it for Japan. He just needed, 50 or 100 donors to cover everybody in Japan. Most of us are not Japanese, although Judy is of Japanese descent. My wife is Japanese. And so they're covered. Thanks to Shinya, we aren't. So we have to do it bigger and better.
Two questions, Irv. In terms of the first technology, what's to stop an educated oncologist going ahead and using the stem cell purification method that you developed to treat patients? Is it simply because the pharmaceutical company bought the intellectual property and have effectively sat on it? And the second thing is...
I'll answer the first one first because
Okay.
it's important. The patents are gone. We happen to have the antibodies I got back from the company because I said the patents will be gone. But the problem with the bone marrow transplanters, the oncologists, is what I said at the beginning. They know that what they do is right. And what we're trying to do is disrupt that. Insurance companies will pay as soon as we show how much cheaper it is to have a transplant without graft versus host disease, without the morbidity of high-dose toxicity. We even had in that first company, Systemics, a large insurance company was one of our major funders, Aetna. But like everything else, as time goes on, the people who are in charge are replaced in a Machiavellian way by others, and they don't know the history, and so...
So could everyone in this room, if they know someone who's got breast cancer, suggest to them there's a different method of treatment that they should, bring to their doctor?
I think they should. It's complicated to do a transplant in the first place. It's complicated to have antibodies that don't carry infectious or inflammatory agents with it. So it has to be professional. It's not in the office. But I would say everybody who knows of somebody with breast cancer that's metastatic, contact Dr. Shizuru. She will lead the clinical trial.
So my second question is something you didn't talk about, but I think is very important for people to hear about, which we talked about last night, which is the number of stem cell trials that people can take part in that are bogus, and how you find out about that, and your kind of view on it.
So I noticed this when I was involved in the leadership of the stem cell field, especially International Stem Cell Society. So if you Google stem cell therapies, you will see the first 99 out of 100 that are probably fraudulent stem cell therapies. So we had to have some way of alerting caregivers and patients how they could find out if it was the real thing or fraudulent. So we started this 10 years ago. We came up with the simplest formula that we thought we could put out to the public and they would know. And if you're writing things down, this is probably worth writing down. We developed a website called A Closer Look that you ask just 2 questions of the person who's going to sell you a stem cell therapy. What was the name of the person who headed the institutional review board at the hospital or university where the very first in-human trial was done? Because their job was not to let a trial be done unless it could be done safely. But they're not there to judge whether it's an effective trial. So that's the IRB. And the second one, whatever country you're in, it has an FDA, its own. And the FDA's job is to approve for therapy those things that are not only safe, but effective. So you ask the second question.
FDA is the...
Get the name of the trial that was done under the FDA that led to the approval. If you don't get both yeses on those, you're almost certainly having a fraudulent stem cell therapy. I talked to an audience about 8 years ago in my hometown of Great Falls, Montana, 40,000 people. It was to the audience, right? So these were farmers, ranchers, working people. And when I got to that part of my talk, there were 185 people there. Two of them came up afterwards. They had already spent what was left of their money for fraudulent stem cell therapies. Now, some of them are even being done by people with MDs. So don't think that just an MD guarantees you won't do something whose only aim is money. We tested, my lab, all of the claims that bone marrow could turn into brain, heart, or blood. It couldn't. If you read the New York Times, a professor at Harvard was fired. They retracted 31 of his papers. And he was hired over the suggestions by me and several people they asked, was he a good scientist? Said, no. I said, he published something that is not reproducible. If I were you, I'd look at everything he's published to see if it's reproducible. I know of at least 5 people who said that, and they hired him. Of course, that was Harvard. That's different than Irvine. But the point I'm trying to make is the force of some people, the political power of some people, the desire for money-making of some people overcomes good sense. And it's hard for the public to know what's real and what's not real, so you just have 2 questions you ask. If you don't get yes on both of them, don't go there. Come on. Matt, you got a question, right? There was a website, I don't know if it's back, it was called A Closer Look, International Society for Stem Cell Research. They shut it down right after we got it up because one lawyer in Chicago said, by what authority are you asking these questions? And I'm afraid to say my colleagues don't have much courage. They shut it down.
You mentioned during your talk that CIRM helped us cross this valley of death, but you also mentioned that the NIH or the federal government doesn't allow this to happen. Could you explain that to the audience further? Yeah,
well, there have been many bills that came up in the time of George W. Bush and Senator Brownback that tried to criminalize any research or any therapy, any doctor who gives the therapy and a patient who receives the therapy if it came from embryonic stem cell or fetal tissue. That was not a scientific or medical judgment. It was a political and religious judgment. Growing up as a Jew in Montana, I really am happy that we have a separation of church and state, because I was always surrounded by people who would have made my life difficult if their religion had been able to be imposed on me and this small group of Jews in Montana. So I campaigned about that, and I'll just say, we thought we had it won. Obama reversed it all. His helper at the NIH didn't enforce what he reversed all. And in this administration, all of us have gotten notes that for every NIH funding application that I've seen so far, they exclude the use of embryonic stem cells or fetal tissue. So that's quite clear that while companies think about money, biomedical research enterprises think about the health of people. The government is not thinking about the health of people as its primary goal. It's willing to be compromised by politics. And politics, especially at this time, is now being carried out by executive action. And we don't even know the hierarchy through whom those latest commands have come through. Have I pissed off everybody yet? There's one more.
Not at all. Oh, wonderful.
Here it comes, wait.
Hi, thank you very much. Can you hear me? Thank you, first of all. I appreciate your lecture. You mentioned in one of the studies where you took the human brain stem cells and put them on the the damaged cord of the mouse. So that's two different species. What about going the other way? Is there any research being done where they're using other species and using that to try to cure human diseases?
Ask the people who are the experts.
That falls into your domain. So it's a great question, right? So let me just repeat that with slightly different words in case everyone doesn't understand. If we can take a human stem cell and treat a mouse, why can't we take a mouse stem cell or a pig or some other species and treat humans? So I'm assuming, right, with the idea that you could avoid all of these complications from an ethical point of view. And the catch is we can make really special mice in the lab. As Irv has pioneered over the years for his blood stem cell research, we can make mice that don't reject these cells because we can engineer them so that they don't have a normal immune system. If we do that to people, then we have a host of problems that ensue, right? That's not an answer in the path that we can go down. And even a cell from me versus Irv, as he used as an example, will reject. That's called an allogeneic graft, one person into a different person. Across species is one level more than that even, that's a xenograft. And so only if we're going into a host where we've already taken out their immune system for all practical purposes can you do that. So going back the other way is not a possibility. The only path is to enable allogeneic transplants, person into person, via some of the technologies that Irv has talked about tonight and advancing the idea of inducing tolerance. But even then, it has to be a person to a person. It can't be across that species barrier. Does that make sense? They get decellularized. So, for example, my father had a mitral valve transplant. That was a pig transplant. But it's decellularized. And so there's no cells there to trigger in so much as we can to trigger that immune response.
And when the valve goes in, the cells from the blood vessels surrounding it make a new coat on it.
Yep. It's probably male to male. Thanks for that, Brian.
Yeah, thanks.
We have one in the way far back there.
Can we get a microphone up there?
Actually, if you want to shout, I'll repeat for you. So in case anyone didn't hear that, the question is, what would be the best stem cell? Would it be an adult stem cell, a fetal stem cell, a mesenchymal stem cell? Is there one that we could pick?
Right. So that's complicated, but before you got to that, right now we know how to isolate blood-forming stem cells from people. So adult blood-forming stem cells would be my first for a blood disease. But we hope, and there are many people in this audience working on it, that we can get embryonic stem cell lines to make blood stem cells, because then you wouldn't even have to get a needle in your vein and to collect the mobilized blood. For some, the fetal tissue is superior. It grows way better. You can't use fetal cells directly because then you'd have to have a fetus for every transplant. And that's logistically even more difficult, even if you had no skin in that game. But some fetal stem cells grow extremely well, and we were lucky enough that includes a brain stem cell. But if you have an endless supply, if it were available, it still would be a process where you couldn't guarantee sterility and a process that keeps you from infection, depending on each dead fetus that follows a woman who's decided on her own without knowing about what the dead tissue would be used for, had agreed. So I think there are barriers. It's not impossible.
Who has multiple myeloma.
You have to turn on the microphone.
Don, can you hear me? Okay, I'm sorry. I have a friend who has multiple myeloma, was just diagnosed. He's 70 years old. Was told that over 90% of his bone marrow is compromised. Is something like stem cell that would be an option for him, or is it too late at this point in time?
So right now, because nobody does pure stem cell, there are people who get transplant from themselves back to themselves after combination chemotherapy. And it seems to give them a window of time. But you're putting back myeloma cells, and they'll grow again with that. There are some combination drugs coming up right now that look pretty good, so they might help. I believe, and Judy will do, because she told me she'll do it, purified myeloma-free stem cells in a trial someday. Right? Later. Or we'll talk about it later.
Sooner than later.
Sooner than later.
Shout it out, Sid.
One announcement, one question. On the issue of direct-to-consumer therapies, we've had a series of eminent speakers on this topic at UCI. We're having one more on February 1st. Jeremy Sugarman from Hopkins will be here talking about the ethical issues in direct-to-consumer marketing of unapproved therapies. So be alert to that. On the ethics side, Irv, I know you did not invent this therapy, but once it had been shown that breast cancer patients' bone marrow contained breast cancer cells, what was the ethical justification for treating people with this?
Because they learned it from their bosses who learned it from somebody else. I think that it really was ignorance that if you put cancer cells back in the body, they will grow. The majority of autologous transplants in humans now give back the cancer along with the blood-forming stem cells to recover from the therapy. The majority. So we're just waiting for a breakthrough that doesn't give you months but gives you years of life after. And I can't explain yet.
So, in a lot of the examples that you cited, there was a need to get rid of the T cells, but I think I read somewhere that T cells are kind of important for fighting off cancer. So I'm curious about your thoughts on that.
That's why I was trying to say carefully, this is for regenerative medicine, to get rid of T cells. You absolutely need T cells, which give graft versus host disease that could kill the patient, costs a lot of money, puts them through hell, to get those few T cells that are graft against leukemia or lymphoma or myeloma, okay? I understand that. Now, we've understood the nature of the T cell receptor since the mid-'80s. We have reagents that can pull out T cells depending on what receptor they have. And it defies my knowledge why the bone marrow transplant community hasn't investigated a way to separate graft versus host disease from graft versus tumor. Now, CAR T cells is doing essentially that. It's providing the T cell therapy. Checkpoint inhibitors, if that's how they work, are trying to reactivate anti-tumor T cells. But don't think that I said you should give T cell-free transplants with no T cell follow-up for malignancy, because you need some way to get rid of that last fraction of the cancer cells the chemotherapy didn't get.
So I think it's maybe a bit late. Don't go away. Nice try. See what a fast break you can make. Somewhere up here, where is behind the curtain? Wow. We have a small gift to say thank you very much for coming today and for participating in our
Where's the camera?
event. And if you could all help me thank Irv for his lecture.